shunt. So if this is the galvanometer, G, you connect a shunt across it. The shunt has a very low internal resistance. Okay. So within the circuit, if you connect a source of EMF, this is what happens. The current moves from the positive terminal to the negative. So when the current gets to this junction, it breaks into two. Small amount of current goes through the galvanometer because it has a very high internal resistance. And because the shunt has a very low internal resistance, the greater part of it goes through the shunt, comes and then joins with this, with the current through the, there's a message, let me see. I couldn't see the message.
Hey, that's
Okay.
good. Yeah, that's good.
All right, so it breaks up, a greater part of it goes through the shunt. A very small goes through the galvanometer because of its high internal resistance. When they get to this junction, they reunite and then comes back to the circuit. So by so doing, you are creating an alternative path which allows maximum current to flow through the galvanometer. The point is that the pointer of the galvanometer will not deflect to this larger current passage, but because that is the initial design of this. The initial design of this is to measure small currents. You are adapting it to look like measuring high current. And so the pointer will not measure this, but the system, as a result of inputting this, what you are doing is that you are allowing more current to pass without damaging the coil of the galvanometer. So the coil of the galvanometer will not be damaged, by the passage of large amounts of current, by the passage of large amount of current. Meanwhile, if this is not there, you can easily damage the coil and the current will not even go through. So by doing so, you are modifying the galvanometer to look like measuring high current. Okay, so that is how to convert galvanometer to an ammeter. Now, the mathematical equation over here is that, one, by connecting the shunts in parallel, the voltage drop across the galvanometer is equal to the voltage drop across the shunt resistor. This is one. And so we can say that IG times RG is equal to IS times RS, where IG is the current coming through the galvanometer. RG is the internal resistance of the galvanometer. Is is the current through the shunt, and Rs is the resistance, that very low resistance of the shunt. Another equation we can always use to solve a problem over here is that by Kirchhoff's law, the source current I is equal to Ig plus Is. So these are the two equations we always use to solve problems in converting galvanometer to an ammeter. This one, of course, equation 1 is the same as this one. And so whenever there are problems you need to solve, these are the two important equations you have to use in converting a galvanometer to an ammeter. Please, any question? Beryl, any question? Andrea, are you okay?
Yes.
All right. Quickly, let's look at conversion of galvanometer to a voltmeter. So this time, we are adapting the galvanometer to look like an instrument which measures potential difference across 2 points. Now, an ideal voltmeter has these features. One, it has very high, or let me use a strong adjective, infinitely high internal resistance. In fact, it must be so high, even to the extent that current flowing through is zero. Must be so high to the extent that current flowing through it, I, is almost zero. That is a feature of an ideal voltmeter. All right. Then let's look at the features of galvanometer. A galvanometer has a very high internal resistance. Not so high as a voltmeter, because this one, the galvanometer plays double function. It measures current, small current, and also measures potential difference. So its internal resistance isn't so high as a voltmeter, but it has a very high internal resistance. The reason for which it will measure small current, and the internal resistance or the potential difference galvo measures is also in millivolts or micro. Milli is 0.001 volts, and micro 0.000001 volts. So this is the magnitude of the voltage it would measure, very, very small. Okay. Now, if you want to adapt this to measure potential difference or to look like a voltmeter, because its internal resistance is high and a voltmeter has an infinitely high internal resistance, we must add some of the resistance to it so that it will be so high to the extent that no current flows through, because that is the quality a voltmeter has. So we must add on to the internal resistance of the galvanometer if we want to adapt it to look like a voltmeter. Please, are we there? Are we okay?
Yes, sir.
Hello? Gerard, are you okay?
Yes, sir.
So we have to add on. And so we connect. This is the galvanometer. Jim. We connect to the galvanometer a device with a very high internal resistance. And this we call as a multiplier. So we connect a multiplier in series with the galvanometer. We connect a multiplier in series with the galvanometer. So this is the source of EMF. Okay, just as over here. This time we connected a device whose internal resistance very, very, very low. So let me bring this here. So IG, IS. Over here, we connect a multiplier in series with the galvanometer. So please note the key elements. This one, we connect a shunt in parallel with the galvo. Over here, we connect a multiplier. And the multiplier would add on to its already high internal resistance so that the internal resistance will be infinitely high to close to the point where current flow is almost zero. Now, when devices are connected in series, they drop different potential difference or voltage. So this is the voltage drop by the galvanometer. This is also the voltage drop by the multiplier. But we all know that for said connection, equal current flows through all of them. So IG is equal to IM. Equation 1. The next equation is that voltage drop here plus the voltage drop here must be equal to the source voltage. So V is equal to VG plus VM. Therefore, we can say that this is IRG plus this is IRM. If I is equal, then we can factorize out RG plus RM. So that this is also IR. I can cancel. So we can deduce over here that for multiplier connected in series with a galvanometer, the total resistance is equal to Rg plus Rm. This is also the equations that are used to solve converting galvanometer to a voltmeter. The related equations that are used to solve problems. Please, any question? All right. So within the week, I'll be sending questions. I'll be sending questions so we could apply whatever we've learned in solving problems. Is that okay? Hello, is that okay?
Yes, sir.
Oh, are we there? Let me know your presence. My voice is already down, so please respond to my call. All right, so let's
position the board. I want to copy the one up there.
when you finish, let me know so we continue. Who is MG? Who is MG? Hey, do I have people in the house?
Yes, sir. Yes.
I'm asking, I'm seeing an unknown identity. Mami Jan, na wane MG, onkasa.
Sorry.
Can I continue?
Yes, sir.
Wrestler, are you done writing?
Mr. I can continue. I have finished.
Okay, so AC theory. Our next area to look at is AC theory, alternating current theory. You see, we just went through some aspects of DC or current electricity. You see, if you look at what we've done so far, the source, if I mute yourself, from what we've done so far, the source of EMF under consideration, we were talking about batteries. So if you look at the circuit drawn, the source of EMF is always a battery. When you have a circuit and the source of EMF is from anything like a battery, then you are talking about direct current. So we have undercurrent electricity, we have DC, direct current, and AC, alternating current. So these are the two types of current we have. A DC, which is direct current, and AC, alternating current. Whenever we are discussing current electricity and the source of the driving, okay, the driving source is anything like a battery within a circuit, then the current in question is DC. So when we talk of DC currents or direct currents, DC, sources of DC are one, when the source is battery, when the source is anything like lead acid accumulators, secondary cells, and on a car battery. When the source is anything like photocell, solar, these are sources of direct current. Direct currents are produced as a result of chemical reaction. Okay, they are produced as a result of
Peter, please,
chemical
I cannot
reaction.
see the second source.
Lead acid accumulator. Lead acid accumulator, car battery. These are secondary cells. So car battery, when you find secondary cells, these are all sources of DC. So the DC is produced as a result of chemical reaction between electrodes and electrolytes. And electrolytes. So when you look at a car battery is just like when you have a vessel, then you have an acid, maybe nitric acid or sulfuric acid. Within the sulfuric acid, this is the electrolytes. Then you insert two electrodes. Carbon. And then within the electrolytes, then you connect a bulb. This is a cell. The first kind of cell. Okay. What's the name? Voltaic cell. Okay. So when you do this, there will be chemical reaction between this is the electrolytes. Electrolyte and electrodes. There will be chemical reaction between the electrolyte and then the electrode, and then current would run through. A battery is just like this. The only thing is that for battery, this is the electrolyte is made as a paste. That black thing is made as a paste. But all these heat sources are produced as a result of chemical reaction between electrodes and electrolytes. When you take car battery is a bigger version of this lead acid accumulator. The little different DC source is the photocell. Photocell, solar. You have this on the top of buildings. Now this is also connected to batteries. There's a wire connecting to batteries. So wherever you find this solar cell, there are batteries. What happens is that the moment the sunlight incident on it, okay, electrons are ejected from this. The solar operates on the principle of photoelectric effects or photoelectricity effects. So when light of appropriate frequency and wavelength incident on this, electrons are emitted. The electrons emission, when the electrons are emitted, they drift, so they have a certain kinetic energy. So the emitted electrons, their motion creates current. A current is as a result of the rate of flow of charges. So when electrons are moved, because they move, they create currents, which passes through the wire and then charges the battery. So the more electrons are removed, the more these batteries are charged. Okay, so that in the night, the charged battery is used to power lamps and other devices. So that is how solar cell operates. Is that okay? So these sources produce direct current. Please, any question?
Yeah.
Yes.
My question is that the photoelectric effect, is it the one causing the electrons to move from the excitation of the electrons to move from one orbital to the other? That's making them release that current.
No. You see, photoelectric effect is the phenomenon whereby electrons are emitted from the surface of metals when light of appropriate wavelength and frequency incident on the metal. Okay, it has a lot of applications. One of it is what I'm sharing with you.
Yes, sir.
Are you okay?
Yes, sir.
All right, so let's look at AC sources. AC, but before we look at AC, let me go into DC a little bit. How does direct current differ from alternating current? I've given you the sources of DC. Let's look at the features of this DC, direct current. We say direct current has one directional flow. It has DC has one directional flow. So if we look at a battery, positive and a negative, when you connect it to a bulb. Conventionally, conventionally, it is agreed that current always flows from the positive terminal to the negative terminal. Current I flows from the positive terminal to the negative terminal. This agreement came up because, you see, if you have water pipe, this is the water pipe or hose lying on the ground. If there's no pumping source which drives the water within the conduit, when you position it like this, the rate at which the water flows will be small. Meanwhile, if you position it like this, the same water hose, if it is positioned like this, because this side is at a higher gradient and this is at a lower gradient, you've created difference in gradients. So water would always flow from this part easily to the lower gradient and not the opposite direction. So water current always moves from a point of higher gradient to a lower gradient and not the other way around. If you take current, electricity, heat, even heat always flows from a region of higher temperature to a region of lower temperature and not the other way around. That is why it is said that if you are feeling hot and your thought is that, let me open the fridge, okay, for cold air to blow to my direction, it is a cos 90 work. No work will be done. Because when you open the fridge, your intent is to receive a cool air, but it will not happen because heat energy always flows from a higher temperature to a lower temperature. So what would happen is that heat energy will be transferred from your surrounding, from your body, from your surrounding, rather into the fridge, and it will defrost the ice. So you rather incur more bill because the system is already cool, iced, but because of the transfer of energy, okay, the ice would melt and it will start all over. So no work will be done. You wouldn't get the cool air because heat energy always flows from higher temperature to a lower temperature. So it cannot be blown from cool to hot. No work will be done. Please, are you following? Human beings or beings?
Yes, sir.
Hey, Andre, who is young rich nigger? Young rich nigger. Who is there? Rich nigger, who are you? So, because of these reasons, water flow, heat flow. That is why it is agreed that, oh, okay, then electric current would also move from higher potential to a lower potential. That is why it is agreed this way. But later, through experiment, we realized that the electrons rather flow from the negative terminal to the positive terminal. Because the mobile free charges within the conductor are electrons. The negative terminal repels all electrons. So they move them away from the negative potential. And because this is positive, the positive attracts the electrons. So whilst this repels them, the positive also attracts them. So the electrons flow from negative to positive. But conventionally, we had all agreed that current moves from positive, higher potential to lower potential. And so because we cannot come back and change this, then it was agreed upon that, okay, then let's accept the fact that current flows from positive to negative, but electrons flow from negative to positive. So that's the difference created. Please, are you okay?
No, please.
Andrew, what's your problem?
Steady, I don't know what is going on. I don't get it.
You don't get what?
Like the whole thing, I'm not understanding.
Andrew, we are looking at DC. Okay. Then looking at features of direct current. Direct current has one directional flow. So if the current flow is always from positive to negative, and every DC source has this one directional flow. When you change the polarity, make this side negative and this side positive, we expect currents to flow in this direction and electrons flow in the opposite direction. That's what I'm saying. So a DC has one directional flow. Either it is from this side to the negative or the other way around. So let's put that feature down. Direct current has one directional flow. From the positive terminal to the negative terminal. This is one feature of DC. Two, it has constant magnitude. The current, the EMF or current, which is the DC, has constant magnitude. So on a waveform, if we are representing a DC, a graph of current against time is like this, straight line. Straight line along the positive or straight line along the negative. either straight line along the positive or along the negative, because I said it has one directional flow. Either the flow is along the positive direction or along the negative direction. So this is how we represent DC. Now, the current or EMF has a constant magnitude. This is what it means. A graph of current against time. So this can be changing time. 0, 1 second, 2 seconds, 3, 4, 5. Now, because of its nature, one directional flow, time can change. So when time is 0, this is the magnitude of the current. When time is 1, this is the magnitude. Time is 2, magnitude. On, and on. So by its waveform, its magnitude is constant. It doesn't change. So a DC has one directional flow. Either it is flowing from positive to negative or negative to positive. So you can draw it here or here. 2, the magnitude of the current or the EMF is also constant, has a constant magnitude. It doesn't change with time, it's the same. So these are the features of DC, direct current. Please, is that okay?
Yes, please.
Let's look at AC. If there is a circuit and the source is AC, this is how we represent the source. For DC, you draw a cell or batteries, long one, short one. If you are talking about batteries are a lot of cells, so 2 or more. So this represents battery. But for AC, in a circuit, this is how we show it. If the source is a DC source, you draw a circle and then this is an indication of the fact that the source is AC. So this is AC source. Connected to maybe a bulb. This is a bulb. This is a DC source. Sorry, AC. Alternating current. Let's look at AC sources. Alternating currents can be obtained from 1, a generator. The generator we use in our homes. Akosomo hydroelectric plants. The generator in our homes, Akosomo hydroelectric plant, is also a generator. So generators, plants are also generators. We can also have AC sources from the wind vane. Even the wind vane, they are all generators. Did I say wind vane? Windmill. The windmill, that big fan which rotates at windy areas, the wind farm. They are all generators. I'll explain to you why they are generators. Then, so generators, plants, and we can also talk of a dynamo. Dynamo is seen on bicycles. Whenever you are riding a bicycle, that thing which is connected to the tire, so that whenever the bicycle moves, it creates or it on the light in front of the bicycle. Okay, it is said that so long as the bicycle is in motion, there is an aspect of it which rotates, which also rotates. And if you be riding a bicycle, then it will also light a bulb in front of it. That thing is what we call as a dynamo. Please, have you seen one before?
Yes, sir.
The girls,
Okay.
you are not talking. Deborah and Co. Priscilla, are you there?
Yes, please.
Contribute. If I ask, respond. I am struggling to even speak, and you don't mind me. Eh? So that is what we refer to as a dynamo. It's a source of DC. So whenever you see a bicycle, the lamp in front of it is powered by that thing which is connected to the back of the back tire, which rotates. If you are a fan of bicycles, you must see one before. All right, so these are AC sources. Now, how is alternating current produced? We talked about the DC. DC, I said that direct current is produced as a result of the chemical reaction between electrodes and electrolytes. Okay. For AC, if you go to Akosombo, what happens is that let me give you the definition before we look at what actually happens. An alternating current is produced when a coil is a conductor. So when a coil rotates at a uniform angular velocity within a uniform magnetic field. So alternating current is produced when a coil rotates at a uniform angular velocity. Or instead of uniform, let me use constant angular velocity in a uniform magnetic field. So when a coil rotates at a constant angular velocity, omega, in a uniform magnetic field, AC is produced. The structure of an AC generator simply looks like this. We have a coil, which is a conductor, placed within a field magnet. So this is a concave shaped magnet, the North Pole, and then another concave shaped magnet, the South Pole. Now within the field magnets, magnets are such that when you shape it like this, it concentrates the magnetic field. We have a coil, which is shaped like a rectangle. So this is connected to an output. The output can be a galvanometer, which measures current. So this is the pointer of the galvo. This is galvo, J. When you connect it to a galvanometer, it can be a bulb, it can be anything which would indicate that current is flowing. Then there is a handle to the ammeter because we want this thing to be rotating. So we give it a handle so that somebody can hold it and turns this. So long as this is what we call as a coil, or it has a technical name, ammeter. So when this thing, these are filled permanent magnets, They have field, these are the magnetic field lines within. So when the coil rotates within a uniform magnetic field and induce current, a current is induced within the coil. And that is how AC is generated. This thing I've drawn is what we call as the AC generator. This is the simple AC generator, alternating current generator. It generates AC. So that is how alternating current is produced. Please, is that clear?
Yes, please.
All right. So I've given you the sources. I've given you how it is produced. How it is produced. Now let's look at the features of AC. The name, its name means that the current alternates. So AC, okay, flows alternating current flows in two different directions. So its direction changes, hence alter. It has a changing directional flow. And so let me add that has a changing directional flow. Two, it has the magnitude of the induced current or EMF also changes with time. Magnitude of induced current or EMF changes with time. So unlike DC, whose magnitude is constant, this one changes. Graphically, alternating current is represented by this. When you plot a graph of current or induced EMF against time, it looks like a harmonic function. That is why we said the motion of electrons within a conductor is also simple harmonic. Alternating, the graphical representation of AC is like this. It's also a harmonic function. So this is how we represent alternating current. We said its magnitude, the induced current, the magnitude of the induced current changes with time. This is what we mean. I'm trying to create changing time. So at time, maybe this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. At time t is equal to 0, the magnitude of the current is 0. At time t is equal to 1, this you can read the magnitude of the current here. At time t is equal to 2, this is the magnitude of the current. At time t is equal to something. Okay, so what we are seeing is that the current starts from 0, increases, gets to the peak or maximum, and then and then drops at this time. Okay, then falls to 0, then increases at the opposite end, increases again to maximum and begins to drop and then falls to 0. So we see the magnitude changing with time, increasing, decreasing, falling to 0, increasing in the opposite direction, getting to the peak, decreasing, and falling to 0, increasing, getting to the maximum, decreasing. So the magnitude of the induced current changes with time. These are the features of alternating current. Please, are we okay? Are we okay?
Yes, please.
Yes, sir.
All right, so that is AC for you. Look at the AC generator. This is the generator. The generator is in our homes. When you hear the sound is as a result of the rotation of the coil. The coil has to rotate. So when you hear the sound, that is what it means. But there's something within which rotates it. That is the motor. The motor rotates and so turns the coil. The rotation of the coil is powered by oil. So when the oil burns, it turns the motor. The motor in turn also turns this. The moment the oil in it is used up, the rotation of this stops and no current will be induced. Akosomo, this is what happens. We want the coil to be rotating, so we will need something which will still rotate it even when we are asleep. And so the energy of the running water is utilized. So the system is designed in such a way that the force of the running water continuously turns this, the ammeter or the coil. Okay, so the Akosomo hydroelectric power station isn't different from this. They have the same operation. All right. So that is the difference between AC and DC. The difference between AC and then DC. You see, one thing you have to take note of is that for AC, unlike DC, where there is an indication of positive and negative terminal, you won't find that in any AC source. So if you pick a battery, there is a positive terminal, there is a negative terminal. So it tells you where to connect the positive, where to connect the negative. If you pick an AC source, there is no indication of positive and a negative. This is the reason. For AC, an alternating current, what it means is that if this is, assuming this is positive, this is negative, a closed circuit, current at one point in time can flow from this side and enters into the negative. one direction. And at another rotation of the coil, the current would always can also flow from the negative to the positive. So the directional flow of the current changes. It can move from left to right. It can also move from right to left. So you can't, because the directional flow of the current is changing, you can't indicate one side as positive or negative. The positive can change and will be negative. Negative can also change to be positive. That is why all alternating current appliances, there is no indication of positive terminal or potential and negative potential. Please, this is examinable. Okay, for all AC appliances, we don't indicate a negative potential and then a positive potential because current flows in both directions with time. The directional the current flow direction changes. That is why we call it alternating current. So at one time, the current can flow from this side, move through this and come here. And when the directional flow is like this, it's like this. You see the galvanometer deflecting to the right because the current is moving from left to right. So the galvanometer deflects in this direction. Okay, at another half rotation of the coil, the direction of the current would vary. Instead of moving from this direction, it will now go this direction. Come through this, come here, enter into it, come this way, and then when it flows from right to left, then the galvanometer would deflect to the left, would deflect in this manner to tell you that the current is flowing in this direction. Please, are we okay? Are we okay?
Yes, please.
So that is why we do not indicate any positive and negative on appliances that utilize alternating currents. All right. Let's end here. Let's end here. We'll continue another time. Okay. All right.
Yes.
So see you later. Another time we'll do. Bye-bye.